This talk is going to be about a secure development process. My name is Philip Åkesson. I'm a security software engineer at TrueSec. I mostly do development in C and C++ and some reverse engineering, security testing and stuff like that. The purpose of this talk is going to be to kind of show you that there's more to secure development than just writing secure code. You need to take security into consideration during the entire development process. And I'm going to pose a lot of questions during this talk. I'm not going to give you all the answers. In fact, I'm not going to give you many answers at all. And since we have quite limited time here, I'm going to heavily compress all of this. I'm going to skip a lot of areas, but hopefully it will still make sense. And this is all based on real-world experiences that we have at TrueSec from auditing and building secure systems. And of course, since I work with C and C++ mostly, this is going to be influenced by that. So if I talk about, for example, the build output as a set of binaries, and you don't have that in your environment, just replace it mentally with whatever you have, and hopefully it still works. And there are several models and processes you can use to improve security in your development process. We have, for example, the Microsoft Security Lifecycle, Security Development Lifecycle, sorry. And there are many others just like this. And what we're going to do here today is kind of similar to this. I'm going to make my own kind of simplified view of this. And again, this presentation is not about writing secure code. This is about everything around that. So we're going to go through each of these boxes and talk a little bit about everything, really. And if you're doing some kind of agile development, which a lot of people are doing, this probably loops back together somehow. So first of all, bootstrapping. This is the one-time actions you do in the sense that you need to adopt a secure mindset. You need to get up to some reasonable baseline, security baseline that you do one time. Of course, it's always good to have some security training, maybe go to a security conference or two, but I'm going to show a bunch of more concrete examples that hopefully applies to everyone here. And since a lot of people work with laptops, a lot of developers have laptops, it's really practical. You can work from anywhere. It's really nice to have. What happens if a developer loses a laptop? If you lose your laptop, what happens? Well, what do you have on it? You probably have source code, maybe confidential documents, password keys, and stuff like that. So how do you prevent that from getting into the wrong hands or getting lost? You password protect your laptop. No, you don't. You encrypt your hard drives. Just putting a password, like a login password, whatever, that's not enough. If someone has physical access to your computer, they will own everything anyway. That's just how it is. So just using a password is not enough. You need to use full disk encryption. That's really easy to do in most operating systems. Windows, OS X, Linux, just enable it. It will be totally transparent, and you will be safe if you lose your laptop. Another thing that may sound really trivial, you really need to keep up to date with patches and security updates. This is, the simplest thing to do, really. And not only your operating system and browser and those really major important components, but also your IDE, all your development tools, stuff like that. Because, I mean, maybe you heard about the, if you've been following the Snowden leaks, maybe you've seen this one recently. I think this was just in the news a few weeks ago. A bunch of researchers at Sandia Labs apparently hacked together a modified Xcode SDK or iOS and OS X SDK, that if you're infected by this somehow, your build environment will start doing all kinds of nefarious things, like producing modified binaries. It will exfiltrate data from your systems and steal keys and stuff like that. And at the end of this presentation, or towards the end, if we have time, I'm going to show a demo related to this. So hopefully we'll have time for that. Back to the really super trivial things. This one sounds like something you tell your kids. Don't go around installing like every cool app you find online. You'll end up with malware eventually, and don't think that won't happen to you. This happened to a developer at HP a while ago. A developer was infected by some kind of malware, Trojan, and HP ended up signing this malware with their co-signing keys, which is not very good. And they ended up having to revoke a bunch of keys and certificates that were also used to sign drivers and other stuff. So that's quite an inconvenience for them. And if you're running as root or admin on your development computer, do you really need to do that? Maybe you can like create a lower privilege guest account or something to do your coding, and then switch to the admin account when you have to install things. Because the admin account is the default on OS X, for example, so that's not needed in a lot of cases. I'm guessing no one really runs as root on Linux, but don't do that. Same for Windows. Another just good tip in general, use virtual machines for everything, really. It's a really nice way to separate and isolate projects. And you also get all the other nice things. You can copy machines around and clone them and save snapshots and stuff like that. So it's really nice to have. So not just for security, but really handy in development in general. And I'm just going to point out that using Docker gives you a lot of these advantages as well, except for the security part. Docker is not used to isolate things securely, so don't do that. Okay, moving on to the second box, development. So during development, you often have to collaborate with people, whether you want it or not. It's something you just kind of have to do. So when working together, you often have servers involved somehow, like bug trackers, wikis, document management, version control systems. And even if you're using a distributed version control system, you probably have a central repository somewhere. And the main question here is, are these servers exposed to the internet? They probably are somehow, even if you don't know it. And are they patched and secure? Are they updated? Do you have someone who's responsible for taking care of that? Some ops people or IT people? Using a VPN to access your servers will of course make things better, but only when used as an addition to other security measures, not by itself. Then you will just get like a highway right into your network, which is good for attackers, of course, and bad for you. So don't replace other security with a VPN. When collaborating on source code, of course, you're using a version control system. I don't think anyone is not using a version control system nowadays. So assuming you have some kind of central repository somewhere, who can access that? Does everyone in your company have access to your source code repositories, or just the developers? That's a lot of places. Everyone with a login in your internal system has access to the source code, and that's maybe not necessary. And even more importantly, who can actually update and push code? Especially to the master or trunk or whatever branch you have in your system, the code that's actually being built and used. So yeah, remember that even if you think you have a remote private repository somewhere, it's probably not as private or secure as you think. You can end up with something like this. happened a while ago. Security researcher managed to exploit a bug in GitHub to add his SSH keys to the Ruby on Rails project, which allowed him to push code to the master branch on GitHub, which probably a lot of people pulled down. And he only added a comment, "This could have been much worse." So yeah, that's something to be really careful about. But ignoring those problems for a moment, of course, there are more advantages to using version control. You get really nice accountability for changes if you have a correctly configured system with access control and separate users for everyone, etc. I'm just assuming that everyone has that by now. And I don't know if anyone remembers this. 12 years ago, someone tried to inject a backdoor into the Linux kernel, and actually managed to get the code into CVS. And it was only discovered when synchronizing CVS against BitKeeper. And they found this and got rid of it. And using a distributed version control system like Git or Mercurial or stuff like that makes this a lot easier to notice. Since you can't really, I mean, if you want to add some malicious code, you don't just add it on top. You don't make it the last commit. You want to hide it somewhere back in the history. You can't really do that with Git, since you will just get new object hashes for every commit after that, right? And since you have multiple copies of your repo, it's distributed, you will notice that it doesn't match anymore. So that's really nice to have. And yeah, kind of related, not really. Using code reviews, mandated code reviews, can really save lives, depending on what you work with. But still, does anyone review your code? This is one of the best ways to catch any type of bug, really. Not just security bugs, but any type of bug. So you should be using code reviews, preferably for every commit or every feature you do, or for every sprint, or for whatever chunk of work you have in your workflow. And another thing to consider is if you do push secrets to your version control system, you should never do that. You find a lot of these online. People pushing private keys, people pushing web service credentials, API keys, stuff like that. And even if you notice immediately and remove your commit, that's too late. It's out there. There are attackers scraping GitHub for credentials all the time. And of course, these are for open source projects on public services, so what do you expect? But the same goes for your private and internal repos as well. You should never push secrets, because then anyone with access to your source code will have access to your keys. Yeah, no good. Moving on, the next part is about integrating different components in your code. Since we're doing this from a security point of view, I'm going to focus on third-party components that you don't have control over, really. You didn't write them, you don't know. Maybe you haven't reviewed every single line in the component you're integrating. So, first question, do you really trust your third-party libraries or frameworks or components that you use? They can become your weakest link if you don't trust them completely, if you don't know exactly what you're doing. You're really exposing yourself here, since each library does increase your attack surface. You're adding additional features, complexity, additional code. And worst case, all of these components will have access to the same thing that your application has access to, your data, your users' data. And remember also that you have to trust the libraries that your libraries trust, and the libraries that they trust, and so on, down the entire dependency chain. And a lot of projects have really complex dependency trees that can be kind of difficult to get an overview of. This is an example from a Java Enterprise project from Maven here. And Java is not really my area. I don't work with that, but I've been told that this is super simple. And so I'm assuming that real projects are horrible compared to this. So yeah, you can only imagine. So do you really need all that code, all those dependencies, all those extra components that contain a bunch of features? Maybe you do. But if you do, you decided that you want to use something, do you really keep up to date with what happens with that component after you've integrated it? Do you check for vulnerabilities, system security fixes, and stuff like that? Do you have someone on your team who's responsible for taking care of that and continuously keeping up to date? Large frameworks often have large bugs. It may seem obvious, but I mean, the more lines of code or the more features, the more responsibility something has, the more bugs you will potentially have. And one really important question is, which version are you using of your third-party libraries? Do you just git clone something and just be happy with whatever you got? You got the master branch, seems to work, that's fine. If you do that, all your developers will eventually end up with different version. That's can make for some really difficult to find bugs if you're running all different versions. And I mean, you should really be using a hard tagged or release version of all your integrated libraries and dependencies. So you get like reproducibility. You can step back and see what did we use 2 months ago, and stuff like that if you need to reproduce all bugs. Do you trust the entity behind the projects you're using? Do you know who's behind them? Is it like a hobby coder coding something in his spare time and just putting it online? Is it a big open source project? Is it like a company who released something and you bought it from them? I'm not saying that one is better than the others, but I mean, it might, it might be a different kind of trust you put in that depending on your project. And lastly, is it actively maintained? Do you get security fixes for the stuff you're using, or do you have to fix security bugs yourself if something happens? Are you maybe using a weird fork of a library? You needed to get some extra nice features. You find a fork that gave you that, or maybe did something extra that was really necessary for your project, and now it has to kind of divert it from the upstream or mainstream, so you're no longer getting the same patches. That's something to be wary of. And this next one you've heard before. I'm going to throw it out there again. Stack Overflow is not a cheat sheet. Stack Overflow has a lot of accepted answers that are straight up dangerous from a security point of view. And that goes, of course, not only for Stack Overflow, but almost everything online and in literature and everywhere. I mean, it's difficult to get security right, and you can find tips and recommendations of really dubious quality pretty much anywhere. And some of my colleagues found critical errors in OWASP recommendations, and that's something you would expect you will be able to trust. But yeah, no. And even if something is not technically wrong, it might still be wrong for you if it's not used in the right context. So like cryptography is a good example of that. It's really difficult to get right, even if you're using like standard algorithms. If you find any recommendations online regarding crypto, you should really check it and double check it and check it again, and then probably not use it and just go for implementation that is tested by real security or cryptographers, really. Okay, moving on to dependency management, after you've decided that you trust all your libraries, you know where they, who's behind them, and you know that you really need all those features. So dependency management is about fetching and keeping and managing them. How do you get your libraries? Where do you get them from? You download them from somewhere online, probably. Do you trust the source or repository? Are you fetching it over HTTP or HTTPS? Is the connection secure? Do you use a local repository manager to cache things or make things more practical? It's something to consider. When you get your dependency, do you verify the contents? Do you check that the dependencies you're actually receiving were signed by the author? Or could someone have modified them, intercepted your downloads, and replaced it with something else? And remember that a hash or checksum is not a signature. It tells you maybe that you got something that's not broken, but it doesn't tell you who made it, who created that file, that data. And if you're using a dependency manager to fetch code, that's really handy when you're doing development. They are available for a lot of different languages. Most of them are just meant to be a convenience, and they don't really implement security in the best ways. So this can be a really good way for someone with malicious intent to get to you. Which brings us to this possible attack, Crossfit Injection. So let's say you have a dependency manager that you're using that has insecure dependency fetching somehow. Maybe it's missing signature validation, maybe it's missing TLS. Then if someone can intercept the transfer and replace or inject code into your dependencies while being fetched, you will use these dependencies and build them right into your product and release that to your customers or clients or deploy it on a server somewhere. And a prime target of that would of course be like a consultancy firm where you have multiple clients. You can just inject code into some build server at the consultancy firm and get that spread to a lot of people. Yeah, so use signature validation and TLS. But then when you have your code and you have all your dependencies securely managed, it's time to actually build something out of it. And when you build stuff, you use a build server. That's really nice to have. But it's also kind of risky to use. You have a lot of stuff on this build server. The server has to have access to your source code and a lot of other stuff. So who can access this? The finished products or any artifact produced by the build server, really. You're going to expose binaries probably on your build server, and that might not be a problem. If you're building like just release binaries, you're probably releasing that anyway. That's why it's called release binaries. But if you do like special debug versions with extra logging, security features turned off, that could be something to be careful about. And of course, you have your source code on your build server. It has to have access to that to be able to build anything. But maybe it's not directly exposed in the interface that people use to log on to the server. It's probably exposed anyway. If someone is able to log into your build server, they will have access to the source code. That's just how it is. But again, most of this is probably on the developers' computers anyway, so it's not that big of a deal, but you should think about it anyway. And of course, you're running automated tests. And if you're not, you really should be. But when you do, make sure that tests actually break your builds on failures. If a test fails, you should not get any usable output. And make sure your tests are actually being run. Don't trust your developers to just like run the test every now and then. That won't happen. Another good thing is reproducible builds. Try to make reproducible builds if you can, meaning if you have identical source code, you will get identical output every time. That makes it really easy to know exactly what you're running, makes it easy to step back to what binaries you had a month ago. You can just pull that code out, build it, and you will get the same thing. Easier to fix all the bugs. If you get a bug report from someone running an old version of your product, just step back, get the same binary, and just, debug that. All right. So you've built something, but this next step can maybe be running parallel to the build step. In some cases, you really should do that. That's the verification step. And I'm going to completely ignore all normal testing and QA here. You shouldn't do that. But from a security point of view, what you want to verify is if you have any security issues, right? So you should run static analysis on your code and on your output, if possible. That's a good way to find some kind of easy to make weird logic errors in your code, but most static analysis tools also give you lots of false positives, so you really need to manually review these results. So even if you're running this as a part of your build process, you can't just look at the output and check a box if there's no errors. You will have like thousands and thousands of errors. It's still good to do. And of course, some basic sanity checks of your build output. I mean, just look at what you're getting. The binary size maybe. If the binary size magically triples in a new build, something is probably up. If you're doing some kind of extra security, like obfuscation, you want to hide some stuff, check that it actually applied. And internal code reviews are, of course, really good. They help a lot with catching bugs and security issues. But some areas, like really security critical components, you kind of want a different set of eyes on that. So you could use, you should use external verification like security testing, penetration testing, and external code reviews where it's applicable, really. And as a general point, good code quality, good code standards help with most of this. It also makes reviews a lot easier and more accurate if you have good code. That's a no-brainer, really. Okay, so you've built your application and you verify that the output looks good, or at least reasonable. Now it's time to sign it. And code signing. What's the purpose of that? Why do you sign your code, your resulting binaries? Well, the purpose is to ensure your users or your clients, customers, that something you built was actually built by you and not modified by someone else or tampered with. So that's a really nice thing to have. But when you do code signing, you have code signing keys. Who owns your keys? Do you have someone on your team who is responsible for code signing, like a manager, or do like all developers have access to your code signing keys? Do you put them on your build server to do it automatically? Yeah, there are different ways to do that. I'm going to go into that in a minute. But these keys, what happens if you lose them? An example of what can happen here is, I guess some of you may have heard about this, but a while ago, a big music app developer, this app for desktop computers and mobile phones, they had to make all their users install a new version of their application, release on the same name, identical application, but as a new, it had a new package name, it was signed by new keys. They just said, go install this instead. That's what we're using from now on. And I don't really have any inside information on that, but it seems like they lost their code signing keys. So you should really keep track of who has access to those. And to do that, you need a structured signing ceremony. So first of all, when you sign, don't do it in the build server. That's kind of important, because if you do, you will end up just like HP when they sign the malware. You will turn your build server into a signing oracle and sign anything that gets into the build server. That's really not very good. But there are various degrees of security you can have when you do your signing. I'm going to list a few here from the least secure to pretty good security, or rather from no security to good security. So first of all, storing your keys in the source code repository together with the source code. That's not good, because then everyone has access to your source code, will have access to your code signing keys, and can sign things and pretend to be you. So that's not good. And again, signing on the build server, turn it into a signing oracle, not good. Signing on select machines. You have select few machines with code signing keys, and maybe a few developers have access to those and are able to sign code and do your release packages. That's not bad, really. That's okay. And using one air-gapped specific computer, it's not connected to any network, it's used just for code signing. That's, now we're getting somewhere. And if you want to be really paranoid, put them on a USB stick, throw that in a safe, unlock it. We'll put your keys on multiple USB sticks, so you avoid device failures, but that's kind of good. But in reality, in a real project, what should you aim for here? For most projects, I think that signing on select machines is good enough, and that should be doable for in most projects. So if you can do that, you should be happy with that. And when you have your build signed and verified and ready, it's time to publish it. I'm not going to go into details here, so I'm just going to say that if you publish to an app store, keep track of your credentials again, your account information. Same as with the code signing keys, anyone with access to these credentials can put things online in your name on this app store, probably. That's something to keep track of. And if you publish stuff to your website as downloads, do you provide secure downloads? Can your users be sure that they have a secure channel to your server? Do they get signed packages? That's a nice thing to offer your users. And for other ways of deploying, if you're deploying server-side code to a server somewhere, it's not. Just make sure your channels are secure and keep track of your credentials. So when you have released something, it's deployed to your customers or users. It's out there. It's running. What happens? Well, a lot of the time, when you run your end product, your application, you have a lot of code that's loaded dynamically that was not part of your original package, maybe. Sometimes you even have code that's downloaded or hyperlinked in from JavaScript, from external sources. That's maybe debatable if that's a good idea. If you're doing like native development or .NET or Java, you have maybe dynamic libraries that are loaded from the file system. Some may be bundled with your application. Some may come from the user system. And if so, do you check signatures on all these libraries? If you don't, you really don't know what is being loaded or what is being run. And that kind of is what I'm going to show a demo about, these dynamic libraries. And this is kind of connecting back to what I showed earlier with the Sandia Labs Xcode malware. So I'm going to show a short demo of how using dynamic libraries in Xcode, the libraries used by Xcode, loaded by Xcode, exploit them to corrupt an entire development environment, resulting in malicious code being injected into the things you build using Xcode. And if you want to know more about how this actually works, there's a really excellent paper by a guy called Patrick Wardle. He presented some nice stuff about that at Infiltrate a while ago. So I'm going to have a link to that at the end of the presentation. Or you could just go to Google and type like dial-up hijacking. It's probably the top result. So let's see. I'm going to switch to the demo here. All right. Okay, so what I have here is a clean install of OS X in a virtual machine. I have installed Xcode on it, and that's pretty much it. So what I'm going to do is, I know that Xcode is loading a bunch of different dynamic libraries on startup. So I picked one of those, and I know that Xcode is looking for that one in 3 different places. And the actual location of this library is in the second location. So what I've done is I built my own version of it that just links in the real one and re-exports it. So I have all the symbols of the real one, and I added some code of my own. And I'm going to put that in the first location. So it's going to be loaded before the real one. And then we'll start Xcode here. We're going to create a new project. We'll do a command line tool. We'll call it test. That's a good location. Okay, so when creating a new command line project, you get some hello world code ready for you. So we're just going to compile that. And when I pressed build here, let's see. Yeah, looks like it's messed up somehow. Let's try that again. New project has 2. That looks like a good location. There we go. I have no idea why that didn't work before. Okay, so when I pressed build here, I don't know if you noticed, this one showed up. And of course, in a real scenario, this wouldn't be as obvious. You wouldn't see any files popping up. You would just have code injected when you build stuff. And when we run it, this one is not in our code. So we have code execution in the release binaries produced by Xcode. And this could be used to like steal passwords or keys or whatever from your users. And it's really kind of difficult to find. You probably wouldn't even know that this code was being injected. It would be hidden, and I mean, yeah, really difficult to find unless you're doing some really extensive static and dynamic analysis of your release binaries. But there is a tool to find out which libraries or which applications really on your OS X system are vulnerable to this. And if you have any that appears to be hijacked, like I did before. This is a new tool created by the same guy who wrote the paper about this, Patrick Wardle. And I'll have a link to this as well at the end. It's called Dynamic Highlib Scanner. Dilib Hijack Scanner. And if you just run this, it's going to find that Xcode is vulnerable, and it appears like this DVT Foundation library was modified or hijacked. So this tool is free. You can get it online if you're using OS X. Get this, try it out. It's really nice to have. It's okay. So what is this doing? If you, I'm going to show you that as well. You have this O tool binary that can show you. Let's see here. I'm going to run O tool on Xcode. It's going to show you some information about the Mac O binary, the executable. Oops. Shit, I have a weird keyboard layout here. Oh, there we go. Okay, so what this tool is looking for is the relative path commands here. This says where it's looking for libraries when they're being loaded. So it's looking for libraries that are placed in one of the R paths. That's not the first one. And any of those are, of course, vulnerable because you can just copy the library and place it in the first one, and then that's what's loaded. And when it said that Xcode was hijacked, that's of course because it found a library in two of these. All right, I managed to get in some weird full screen mode here in my virtual machine. Does anyone know the key command to get out of that? There we go, I think. No? Sorry? There we go. I'm just going to close it. There we go, and back to the presentation. Okay, so that's something that can happen to your applications as well. I mean, if you're developing for OS X, same thing kind of works on Windows in a slightly different way. I mean, it's how dynamic libraries work, really. I mean, there are ways to do it on most operating systems in one way or another. So to avoid this, what should you do? You should verify your code. You should check for signatures. You should verify signatures. You should verify your script sources. If you're loading JavaScript, you should really stop just loading that from external sources. You'll have no control over that, right now at least, because sub-resource integrity is actually coming to HTML, maybe. So if you do web development, you use JavaScript, you include external sources. This one is something to keep track of. There's a draft out right now, and it's going to look something like this. You can link external resources and add a hash to it, and if the hash doesn't match, it won't load. That's really nice. If you're serving this over HTTPS, of course. Otherwise, it will just not matter at all. Okay, so we're a bit over time, but it's time to conclude this anyway. I'm just going to finish this off by asking a bunch more questions. That seems like the most reasonable way. So, are your machines secure? Your development machines, your servers? Who has access to your source code? Who has access to your binaries? Do you know? Are you using code reviews? Do you know where evil code can get injected into your products? Using Crossfit Injection, using dilib hijacking, using any other kind of way. Is your identity safe? Your identity as a signer, your identity as a publisher? Yeah, that's all I had really. I really don't have time for any questions, but if you find me afterwards, we'll deal with that. And here are the links. Thank you.